determination of spring constant. So the aim of this experiment is to determine the spring constant in series combination as well as the parallel combination. So the apparatus required for this experiment is the spring. So I have taken two springs and the scale and also this weights. So the each weight which carries 50 grams, and this is also 50 grams including or along with the hanger. Okay. Constant means, spring constant means, so when mass is attached to this one end of the spring, so the restoring force which acts on one direction and displacement causes on the other direction. As per the Hooke's law, it is given by the force is directly proportional to displacement, or F which is equal to K into X, or F restoring force which is directly proportional to X, or F which is equal to minus K into X. So this negative direction means it is exactly opposite direction, or this K is nothing but it is the spring constant or the stiffness constant that we have to find in our experiment. So force divided by unit displacement. Okay. So before that, going to series and parallel combination of the spring, first we should determine what is K1 or spring constant 1 and spring constant 2 we have to find. So we have two formula, that is in series spring constant, that is K series which is equal to K1 K2 divided by K1 plus K2. So this is the theoretical formula that we have learnt in the theory classes. And for the parallel combination of the spring, it is given by K parallel which is equal to K1 plus K2, that unit is Newton per meter. Study the spring constant K1, so that we have used two springs, so I can take first spring so to determine K1. So I am attaching this spring holder and hanging and applying certain dead load. So dead load or initial load I have taken, it is 100 grams. So the each carries 50 plus 50. So this is the initial load. So because of this initial load, it stretches certain distance. So the distance is value is 11 centimeter. So after attaching certain load, that is 100 gram mass, so the length of the spring becomes 11 centimeter. So now you have to enter it in the tabular column. So here the tabular column to find K1, because I am finding the spring constant K1. So the pointer reading with initial load W means initial load or dead load, I have taken it is 100 gram, and initial length it is 11 centimeter. Okay, so for 100 grams dead load it is 11 centimeter. Now again I am applying this W plus 50 grams, means W is initial load that we have to leave, only we have to concentrate 50 grams. So again further I am increasing it by 50 grams. Again, as per the Hooke's law, force is directly proportional to displacement. It displaced to some other position, that is 14.3. Initially it is 11 and now it becomes 14.3. Again you have to note up. So the pointer reading, it is B. Pointer reading B in terms of centimeter, it is 14.3 centimeter. After applying 50 gram, the stretch is 14.3 centimeter. Initially it is 11 centimeter. After I am applying 50 grams weight, it becomes 14.3 centimeter. Then what is the total stretch? So the total stretch is final minus initial value. So 14 minus 3 divided minus 11 centimeter, that is spring stretch which is equal to X which is equal to B minus A. B is 14.3 minus A. So I got 3.3 centimeter. Then we can find force, because if you want to find K1 which is equal to F divided by X, then force which is equal to mass into acceleration due to gravity. Mass is 50 grams. So in terms of kg, because we are measured in terms of Newton SI units, kg it is 50 into 10 raised to minus 3 multiplied by acceleration due to gravity, it is 9.8. Answer is 0.49 Newton. So the force which is equal to 0.49 Newton. And the spring constant, it is given by F divided by x, F is 0.49 divided by x value is spring stretch, that is 3.3 into 10 raised to minus 2 because it is centimeter. So answer in terms of Newton, it is 6.33 Newton. 6.33 Newton. Same thing again we have to find for W plus 100. Already I have applied 50 grams. Next is again I am putting another 50 mass, so that again it will stretches and comes to 17.8. So it comes to 17.8 centimeter. So the spring stretch x, which is equal to b minus a, initially it is 50, next again I am applying another 50, so the total stretch is final minus initial value, that is 17.8 minus 11 centimeter, it is 6.8 centimeter. So the total stretch is 6.8 centimeter for the load of 100 grams. Then again what is force? Force, which is equal to mass into acceleration due to gravity. Mass is 100 multiplied by 9.8 into 10 raised to minus 3 because in terms of kg. So 9.8 into, or we will get 0.98 Newton. Okay. Now again what is force? Force, which is equal to 0.98 divided by 6.8 centimeter. So answer is 14.41. So 14.4. Similarly, you have to repeat for. Okay. Further we have calculated for the remaining things, that is, so after applying load 100, so the answer is 14.41. Next for 150 stretch is 21.3, the calculation it is 14.27, and for 200 mass weight it is 14.62. So the average spring constant K1, which is equal to, so add this divided by 4, you will get 14.90 Newton per meter. Okay, so this is the K1, and similarly we have to find for the second spring K2. Same experimental procedure we have to follow for the second spring. So that is initial load, it is W gram, W which is equal to 100 grams, and the stretch is 10.8 centimeter because length is not same, it depends upon the spring. Initially I have got 11, but now we have got for the second spring it is 10.8 centimeter. Same experimental procedure we have to repeat for the cases, that is W plus 50, 100, 150, 200, and we will get the average K2 value as 14.89. So the K2 value we have 14.89. Now we can calculate through this series and parallel spring combination as per the theoretical concept. So we have two formula, that is K series, which is equal to K1 K2 divided by K1 plus K2, value is 14.90 as K1 and 14.89 as K2. So the answer is 7.47 nanometer. So this is spring constant in series combination in theoretical. And we can also calculate through parallel combination, that is parallel, it is given by K1 plus K2. So after adding this we will get 29.79. So this is the theoretical formula we have, and we got these results. And now our aim is to verify in terms of what? Practical consideration. So this we have find K1 and K2. Same thing we have to find the parallel combination. So as in the diagram, K1 is same, K2 for the single spring. K series, there are the combination, two springs. Same thing, the experimental setup as observed here. So this is spring 1 and spring 2. So the spring 1 I have connected in terms of series to spring 2. And the same load, that is dead load. So initially in all cases I have used it is 100 grams as a dead load. Now the same thing we have to identify the scale. So the initial length, again we have to monitor here, because the two spring it will stretch. X1 is also stretches, X2 is also stretches. So the total distance it is X. So it comes to 25 centimeter. The enter in here. Tabular column. Pointer reading 100 grams, it is 25 centimeter. Next, W plus 50 grams. So again I am applying another 50 grams load. So the spring stretches and comes to 31.7. 31. Comes to 31.7. Okay. Now what is the calculation? Again, if you want to find spring stretch, the 31.7 minus it is 25. So you will get 6.7 centimeter as a spring stretch. So the force already we have calculated with respect to same load. Same thing, 50 multiplied by 9.8 into 10 raised to minus 3, you will get 0.49. So the force which is equal to 0.49 divided by 6.7 centimeter. 6.7 centimeter. So the answer is, we will get 7.31 as initial case. So again we have to do it for the 100, 115 and 200. So initially the first value I am comparing with the theoretical value. I got through practical, it is 7.31 in series spring constant, and the same thing in theoretical concept I got that is 7.47, almost nearer, hence our experiment and theoretical concept matches. Okay. Now further we have calculated for the other 3 weights, that is 100 will get 7.42 and 150 it is 7.35, and the total average it becomes 7.36. But in case of theoretical experiment we got 7.47, almost it is matching. Now we will look into the parallel combination of the spring. So already we have two springs, so spring 1 and spring 2, and I can consider it to joining the two springs S1, K1 and K2, same thing. So I can hold it to spring holder, and now I am applying the dead load. So the dead load I have taken as 100 grams. So 50 plus 50. So because of that it will stretch, the uniform stretch. So here it comes to 9.3 centimeter. 9.3 centimeter. Okay. So I am applying W plus 50 grams so that it will stretches to 11 centimeter. So 11 centimeter. Initially it is 9.3 centimeter and this becomes 11 centimeter. Total is 1.7. 11 minus. So it is 1.7. Therefore the force is same, 0.49 Newton. So the calculation 0.49 Newton divided by 1.7 centimeter. 1.7 centimeter. Centi is 10 raised to minus 2. So we will get 28.82 Newton per meter. But in case of our theoretical concept, it is 29.79, because further we will see. Further, if you calculate for 100 grams, so the K in parallel it will get 29.6, and for 150 it is 30, and 200 it is 29. So the total average for K parallel it is 29.37. So now result, the spring constant for spring is to be are to be found, that is K1 which is equal to 14.90 and K2 is 14.89. So the combination series and parallel, for series theoretical concept it is 7.47 and through experimental it is 7.36. And same thing for the K parallel. So by theoretical concept it is 29.79, by practical we will get 29.37. So this is about the series and parallel combination of spring constant.